Hey everybody, it's Tuesday, October 27th, and as we alluded to yesterday, today is a glorious day. And that's because we are done with motion and we are moving on to the next unit. And the next unit is all about forces. And so our discussion about forces is going to be significantly more substantive than our discussion about forces in honors physics. But before we get there, we have to talk about something that applies specifically to forces, but also applies to other vectors. And so this is a pretty good, I think, transition lesson between what we were talking about in the last video, which was all about relative velocity, to what we're going to be talking about through the next few weeks, which is about forces. So as you can see here in the aim today, it says, how can we use concepts of vector addition to solve problems? And so this is going to be the first of many lessons that we can apply to our discussion about forces. When we get into this discussion about forces, we're going to be talking about, in general, what a force is and how we can use our understanding of forces to talk about how it affects the motion of an object. We'll talk about Newton's laws, and then we will take that into much more detail than we did in the honors class. For today, we are essentially going to pay very close attention to the fact here that a force is a vector, which I'm sure is something that you remember from honors physics, and that because it is a vector, it combines in ways that other vectors combine in. And so to start us off with the discussion here, we should take a brief look at some definitions. And the first definition we're going to take a look at is the definition of a resultant. And the key thing to remember about a resultant, I think, is that a resultant is exactly as it sounds. A resultant vector is the single vector that is equivalent to the combined effect of two or more vectors. And so when we add two vectors, or we subtract two vectors, or we combine two vectors in any way, we call the sum, the difference, the product, whatever the combination is, we call it the resultant vector. Now today we're going to be mostly focused on addition, and so I'll just write here, we call the sum the resultant vector. And so the resultant vector, notice, is called the resultant in a totally unsurprising way because it is the result of combining vectors. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So you've seen some examples of vector addition already. When we left off in yesterday's video, we were talking about relative velocity. And the thing to realize about relative velocity problems is they are essentially vector addition problems. When you're finding the relative velocity of something, you're basically just combining, by addition, the vectors that are given in the problem. And so for one-dimensional vector addition, there are basically two examples. There's an example where the vectors are in the same direction, and examples where the vectors are in opposite directions. And what we can say as sort of a common rule for both of these examples, which we definitely saw for sure in the video yesterday, is when vectors are oriented in the same direction or in the opposite directions, notice both examples of one-dimensional vector addition, to find the resultant vector, you add the vectors with their individual signs, which represent their directions. So in all of these vector addition problems, we're going to use the idea, again, of a coordinate system, and we're going to make sure that we follow the conventions of the coordinate systems that we've always been following for the whole year. So notice the two vectors in the top image are shown to the right, and so we call those positive. We add them up, we get 5 plus 5 is 10. The vector that's 5 units long in the bottom image is to the right, and so we call it positive, but the 15 unit vector is to the left, and so it is counted as negative. And so we have to add them with the individual signs when we're finding the resultant vector. Take a second to pause this video here and sketch those images and write this note down, and then we'll move on. So the next example of vector addition that we need to discuss, obviously, if it's not a one-dimensional vector addition problem, is a two-dimensional vector addition problem. But before we do that, let's just very quickly make note of the fact that the equation you use for a one-dimensional vector addition problem depends on the vector you're talking about. So if we're talking about velocities, sort of like how we did yesterday, we can just say the resultant velocity, and we'll write v with the subscript r, is v1 plus v2, where we're adding them with the signs. And so I'll just write here in parentheses, resultant velocity. And if we're talking about a force, then of course it's the same idea, because no matter what kind of vector it is, the whole point here is that all vectors combine in the same way if they are in a one-dimensional situation. And so this would be the resultant or net force. And notice now, net is a word that we almost exclusively use for forces, but you could just as easily use the word resultant and use the symbol for resultant, which is that subscript r, and write it like that. It really doesn't matter. And this is true whether we're talking about velocity or forces or accelerations or any other vector. They add in the same way. But if we're not talking about a one-dimensional problem, we're talking about a two-dimensional problem. And this is where we are going to take this beyond what we talked about in the honors course, because if it's a two-dimensional problem, there are actually two different kinds of two-dimensional vector addition problems. The kind of two-dimensional vector addition problem that you're probably already familiar with is the kind of two-dimensional vector addition problem where the vectors are at right angles. And so let's say these vectors, just to make it clear, let's say these two vectors are 3, and let's call them velocities, why not? 3 meters per second and 4 meters per second long. When two vectors are at right angles, like this, as shown in the diagram here on the right, then the resultant vector effectively represents the hypotenuse of the right triangle that's made up by these vectors. And so the idea here is pretty simple. I'll actually just go ahead and write this here because I can fit it. The resultant velocity, if we're talking about velocities in this case, is the Pythagorean sum, as we call it, of the two vectors. And so we'd have the resultant velocity is equal to the square root of v1 squared plus v2 squared. And very similarly, as we just showed before, the net force, or the resultant force, would be the Pythagorean sum of f1 squared plus f2 squared. Same deal. Whenever vectors are at right angles, the way we find the resultant vector is by using the Pythagorean theorem. And that, I think, makes a heck of a lot of sense. Because if we align the vectors tip to tail, as is shown here, where we take the arrow, called the tip of the one vector, and align it to the tail, or just the non-arrow-headed side of the other vector, we see a perfectly reasonable right triangle. And so it makes sense that these things follow the rules for right triangles, in that the hypotenuse is the Pythagorean sum of the other legs. Now, notice when we began this discussion of two-dimensional vector addition, I said that there are two possible cases for a two-dimensional vector addition problem. The other case, which I'd like you to sketch, actually, the other case of a two-dimensional dimensional vector addition problem is when the two vectors are not at right angles. If they're oriented like this, for example. And so when vectors are oriented like this, we need to use a much more mathematically detailed method for solving for the net force or the resultant vector. So what we'll say here is note, when vectors are oriented in a 2D configuration and not at right angles, to find the resultant vector, we must either, and I'm going to write here, number one, use the component method, which is an analytical method, or in other words, math, or use a graphical method by making a scale diagram. Now, you don't actually have to do the scale diagrams for this course, but I am going to at least show an example of it. I'm not going to have you do it because I'm assuming you probably don't have access to graph paper. And either way, it's not on the AP test, so it's not worth using our time for. But at least, oh my God, I did it again. But at least you can get a sense of how it works and how it ends up giving you the same answer to the problem if you'd like to see it. And so when vectors are oriented in a 2D configuration and not at right angles, to find the resultant vector, we must either use the component method, which is a mathematical or analytical method, or we can use a graphical method. They'll give us the same answers, as we'll see, but we need to use one of these two methods. Take a moment to pause this video here and write that down, and when you hit play, we'll move on. So before we move on here, I just want to take a second so as to not confuse anybody by the terms I'm using in case you forget. In a lot of these problems, because we're talking about forces, I want to take a second to just talk about forces. The symbol for a force is F. And a force, remember, I'm sure this is not news to anybody, but a force is any push or pull exerted on an object. That's as best as we can do for right now. Now, remember, what we are talking about is Newtonian physics. So those of you who may be seeing things on YouTube or whatever about forces, as our conception of them in 2020 has altered the way we think about them, that's not what we're talking about here. We're talking about a conception of forces in like the 1800s. Of course, Newton was alive in the 1600s. This conception of forces existed really all the way until the early 1900s. But it's important to realize we're talking about Newtonian physics here. And so for now, we are still in like a 1700s, 1800s framework for understanding how these things work. And in that framework, we just say a force is any push or pull exerted on an object. And the last thing we'll say here, which is really the only thing you need to know for now, is that the unit for force is a Newton, because you will see that here in a minute, which is given the abbreviation uppercase N. And we'll just say here also, which should not be a mystery based on everything we've said so far, but a force is a vector. So basically, all you need to know about forces, clearly because this is the first day we're talking about them, is that a force is a push or a pull, the symbol is an uppercase F, the unit is an uppercase N, and it's a vector. Because what I'm going to do right here is I'm going to show you the steps involved in the analytical method, and then we're going to solve one. And you'll see in these examples that we're going to be using these ideas given here. Okay, so the analytical method, or the component method as it's called, has 5 main steps. I want you to write this under the heading component method. So the first step, To solve for a resultant vector, and that could be a force, a velocity, a displacement, an acceleration, whatever you want, the first step is that you need to resolve each vector into its x and y components. And this next part that I put here is extremely important. You need to make sure you reference the angle to the positive x-axis. Now, we actually already talked about this when we were talking about finding the angle for projectiles and how to find the components for a vector. But this part is very important. You need, when you're resolving each vector into its x and y components, you need to make sure you reference the angle to the positive x-axis. Step 2 is you need to add the x components for each vector. And this will be the x component of your resultant vector. And so we can write here a simple little equation for that. We can just say like f net, you could write fr also, f net x would be f1x plus f2x, etc., depending on how many forces there are. So the net forces, or the resultant forces, x component is going to be just the individual x components added together for all of the vectors. Very similarly, to find the y component of the resultant, you add the y components for each vector. This will be the y component of your resultant vector. And so in the same style here, we can actually write f net y equals f1y plus f2y. And so now it's important to realize here, like, what we're doing actually makes a lot of sense. And I hope you see where this is going. We're going to have a bunch of different vectors. Now, usually in these problems, it's 2. But we have a bunch of different vectors. And so we're going to break them up into their x and y components. And we're going to add the x components, and we're going to get an x component of our resultant. And we're going to add the y components, and you get a y component of your resultant. You see where this is going? Our x and y components are at right angles. And so the fourth step is to use the equation, the resultant equals the x component of the resultant squared plus the y component of the resultant squared, to determine the magnitude of the resultant. Notice I decided to use r's here on this slide because I want you to realize it could be either f net or r, and of course it depends on what kind of vector you're talking about. But if we're talking about forces, we can say your resultant could be written as f net equals the square root of f net squared, f net x squared plus f net y squared, and then square root. So we're finding the x components, adding them all up, finding the y components, adding them all up, and now we have the x and y components of our resultant. And so we're going to use the Pythagorean theorem to find the hypotenuse of that triangle. And that is our resultant. And if we're talking about forces, we usually refer to that as f net. And then the last step, of course, I hope you all realize, because a vector is a measurement which has both a magnitude and a direction, is going to be to find that angle. And so step 5 is to use the equation theta equals the inverse tangent of the y component over the x component to find the angle. And notice the reason why we're using y over x, again, and we discussed this when we were going over it, is because the y component of the resultant is the opposite side of the triangle, the x component is the adjacent side, and tangent is opposite over adjacent, and so we get y over x. And that's it. And just to be clear, because the word is used a heck of a lot on this slide, note, in this and all contexts, the word resultant refers to the result of the combination of 2 or more vectors. I'd like you to take a minute here to pause this video and finish writing that down. This is very important. And when you hit play, we'll take a look at an example of one of these. Okay, let's take a look at a problem. We might as well apply this here to see how this actually works in the context of a real problem. And so in this problem, and I'd like you to go ahead and sketch this in your notes, in this problem we have two forces, as you can see here from the unit, oriented like this, with their angles from their respective axes given in the diagram. Before we go ahead, I actually want you to take a second to sketch this. I want you to pay particular attention to the angles that are given here, and I want you to pay particular attention to the length of the vectors, because notice the 500 Newton vector is a little longer than the 400 Newton vector, and that's because the lengths in these diagrams show you the magnitude of the vector. So take a second to pause this video here and sketch that diagram, and when you hit play, we'll go ahead and solve this. So as you could see here, I'm going to just use this vector first, just because. It says here we have a 400 Newton force, and that's 400.0 newtons, and that acts at an angle of 50 degrees. So we have 400.0 newtons. Notice that lets you know that every single number we get from this problem should be given to 4 sig figs, because we don't really care about the angle. So we'll call that F1, is 400.0 newtons, and theta 1, our angle here, is going to be 50.0 degrees. Okay. And it says here our second force is 500 newtons. And notice, they tell us this angle is 40 degrees. But I don't actually care about that angle. What I need to know, and I'll do this in a different color just to show the contrast here, what I need to know is this angle. And the reason why I need to know that angle is because, as it said in the steps, and let me just go back, the angles need to be referenced to the positive x-axis. And the reason why we said the angles need to be referenced to the positive x-axis is because we need their signs to work out correctly, which you'll see in a couple minutes will prove to be very important. So we'll say that F2 is 500 newtons, and we'll say that theta 2 is 140 degrees. Remember, there's 180 degrees between the negative x and the positive x-axis. And so if this one is 40, 40 plus blank equals 180, and of course the other angle is 140. So we'll have here F2 is 500.0 newtons, and theta 2 is 140 degrees. We'll keep it to 3 sig figs since the original angle was given at 3 sig figs, and we're looking for F net. So, following along the steps of the component method as we just saw, and I'll just flip back to it again, is we need to resolve each vector into its x and y components. And so, this is a lot of writing. When you're doing this, you want to be smart about the way you are doing this, because this is long and you just want to make it quick. So what I do is I write f1x equals f1 cosine theta 1. Then I write f1y. I keep the 1's and 2's together. f1y is f1 sine theta 1. Remember, sine cosec's. The sines go with the y's and the cosines go with the x's. f2x is going to be f2 cosine theta 2. And f2y is going to be f2 sine theta 2. Then I write my equal signs. I want to keep this as organized as possible. And now I'm going to punch in my numbers. And so F1 is 400 newtons, 400.0 newtons. And the cosine of theta 1 is going to be the cosine of 50.0 degrees. I'm going to close that up. I'm going to write equals, and I'm going to move on. Why am I moving on to another one before getting the answer to that? Because I don't want to write that down, put my pen down, pick up my calculator, type it into the calculator, get my answer, put my calculator down, pick up my pen, write the answer down, move on to the next one, plug in the numbers, put my pen down, pick up my calculator, type it into the, you see what I mean? So if you just write all the things down once, then you can type all 4 numbers into your calculator at the same time and then just write down the answers. And so here, I'm just going to continue along. 400.0 newtons times the sine of 50, 50.0 degrees. And then moving on, I have F2 cosine theta 2, so that would be 500 newtons times the cosine of 140 degrees. And then I have 500 newtons F2 times sine theta 2, which is going to be times the sine of 140 degrees. Okay. And so then you go to your calculator, and then you're just going to type these things in quickly. 400 times the cosine of 50, 400 times the sine of 50, 500 times the cosine of 140, and then 500 times the sine of 140. And so notice here a couple of things. For the first vector, the 400.0 Newton vector, we have 2 components which are positive. And that makes, whether you realize it or not, a heck of a lot of sense. And the reason why that makes sense, and let me just get rid of these drawings on here. The reason why that makes sense is because the x component of this vector goes this way in the positive x direction. So it makes sense that that's positive. And the y component of the vector goes up in the positive y direction. And so it makes sense that that's positive. Notice that's the same thing for the y component of this vector over here. It points straight up in the positive y direction. But if you notice, the x component of the 500 Newton vector points to the left. And because it points to the left, it should be negative because it's not pointing in the plus x direction. It's pointing in the negative x direction, and that's the idea. And so notice, and I'm going to keep these here for a second. Notice if we had 500 times the cosine of 140, we get negative 383. But if we do 500 times the cosine of 40, which was what the angle was with respect to the positive x-axis, or excuse me, with respect to the negative x-axis, we don't reference it to the positive x-axis, it's going to give us the right number, but it gives us the wrong direction. And so that's the reason why you want to reference all of these angles to the appropriate axis. And so going through with our answers, keeping them all to the appropriate number of significant figures here, which is 4, 400 times the cosine of 50 was 257.1 newtons. 400 times the sine of 50 was 306.4 newtons. 500 times the cosine of 140 was negative 383 newtons. And 500 times the sine of 140 was 321.4 newtons. So now you have your 4 components. And so according to the next step in the list of steps, we need to add the x and y components for the vectors. And so we'll go ahead and do that now. Add the x and y components. And so the first thing we'll do, and for no particular reason, we'll just do the x components first. So f net to x is equal to f1x plus f2x. And that gives us f1x, 257.1 newtons, plus F2x, which is negative 383.0 newtons. And when we do that, we get an F net x of negative 125.9 newtons. Now, obviously, how this answer comes out depends on what the size of your individual forces are and what angles they're oriented at. But I think that answer makes a lot of sense because notice the force going to the left and the force going to the right are almost at the same angle. If you typed into your calculator, and I'm not going to pull it up on the screen here, I'm just doing this with the calculator I have right next to me, the cosine of 40 is 0.766. The cosine of 50 is 0.642. So they're different, but they're not that different. And so the fact here that the 500 Newton vector is considerably longer than the 400 Newton vector is what really is making the difference in terms of the size. So because the x component of the 500 Newton vector is longer and it's negative, then we should expect our F net x to be negative. Because you have to imagine in all these problems as two people pulling on ropes trying to like pull an object. And if somebody pulled 500 newtons this way and somebody pulled 400 newtons that way, we would expect the thing to go up, but we would also expect it to go a little to the left because the person pulling to the left is pulling harder than the person pulling to the right. So that's our F net x. Our F net y, same style of equation here. Our F net y is going to be F1y plus F2y. And when we do that, we get 306.4 newtons plus 321.4 newtons. And when you do that math, you get 627.8 newtons. So there's our F net x and our F net y. And so just to be totally clear about what we're saying here, that's the wrong way. But just to be totally clear about what we're saying here, we now have the x and y components of our resultant vector. We know here that the x component of the resultant to the left is going to have a magnitude of 125.9 newtons. And going up, notice a lot longer because it's a lot bigger, the y component is going to be 627.8 newtons. And so that means our hypotenuse is going to be pointing somewhere up and to the left, which we already said was exactly what we would expect, that this vector is going to act up and to the left. And so how much that is and how much up and to the left that is what step 4 and 5 are for. And so notice step 4 on that list of steps was to find the actual magnitude of the resultant, which the equation, the actual magnitude of the resultant. And so the equation that we'll use for that is F net equals F net x squared plus F net y squared. And so plugging in the numbers here, we have F net equals the square root of F net x, which is negative 125.9 newtons. We square that, plus 627.8 newtons, which is our F net y, and we square that. We put that all under the radical, and when you do that math and you plug in those numbers and you make sure you square and square root, and you put parentheses around this because the fact that it's negative means when you square it, it should come out to be positive, we get 640.3 newtons. And that's our F net, 640.3 newtons. But of course, we have not solved for the whole F net yet because a force is a vector, which has a magnitude and a direction. And so to finish this one off, we want to find the angle here. And as we said, the angle is the inverse tangent of f net y over f net x. And so that's going to be the inverse tangent of f net y 627.8 newtons over negative 125.9 newtons. And when you do that, this part I want to show here, we're doing the inverse tangent. We're doing the inverse tangent of 627.9 divided by negative 125.9. And I'm going to check that I'm in degrees before I hit the enter button. And when you do that, you get negative 78.66 degrees. And that's a problem. Because if we look at the actual diagram here, and we make sure we're interpreting the angle correctly, negative 70 something, negative 78.6 degrees is 78 degrees below the positive x-axis. So that would be like over here. And that's definitely wrong. Because if you're saying somebody pulls up into the left and somebody pulls up into the right and it's going to go down and to the right, makes no sense. The angle is actually going to be over here. And I hope you notice the relationship now between this one and this one. And so we're going to write down the answer and then write down a little note. The answer here for our angle is going to be 101.3 degrees. And our little note here is going to say when f net x is negative, add 180 degrees to your angle. And I'll write to your calculated angle. And I think the main idea here for you all to remember is it's not supposed to be that hard for you to figure out approximately which direction your answer should be in. And so if you recognize that your answer is supposed to be in the second quadrant, and you solve for an angle, and the angle is in the fourth quadrant, then you should just realize you got to add 180 to it to flip it around to make it in the right direction here. And so to make sure we are totally down with that note, when the x component of the resultant is negative, whatever value your calculator gives you must be added to 180 degrees. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at one more of these before we go. Now, before we go ahead and look at the next one, I just want to very quickly look at the results from the graphical solution to the problem. So in this solution to the problem, I've created a scale diagram. Again, I'm never going to ask you to do this because you're never going to have to do this on the AP test, but I just want to show you very quickly what it looks like. I decided to make my scale for this question 50 newtons is going to be equal to 1 centimeter. And I used a protractor and a ruler to make this drawing. So because F1 was a 400 Newton vector, made that 8 centimeters and drew it at an angle of 50 degrees. Notice that's 50 degrees above the positive x-axis. Then F2, because that was 500 newtons, I made that one 10 centimeters and drew that 40 degrees above the negative x-axis. And so basically, because you're starting this vector from the tip of the other vector, you basically make a new x-axis and make your angle there at 40 degrees. And then we draw in our resultant by connecting the starting point of the vectors, basically the origin here, to the tip of the last vector. And so notice it's pointing about in the right direction. It looks like it's about the right length. You make your measurement of that vector, and I measured it to be 12.8 8 centimeters long, and using the scale, notice a nice little like factor labeling or dimensional analysis unit conversion there. 12.8 when you convert it to this Newton measurement here by using 50 newtons per centimeter gives me a resultant of 640 newtons. Pretty good, considering the analytical method gave us a resultant of 640.3 newtons. And of course, I want to go ahead and measure that angle. And so I measured the angle here between this resultant and the x-axis down here. And notice the y-axis is going to be 90 degrees away from the x-axis. So I know already that this is pretty close. But when you measure it, I actually got 101.6 degrees. And so the idea is the graphical method has a lot of imprecisions because, you know, we're drawing the things by hand and there's some uncertainty in the measurements we're making with the rulers, etc. But the point here is these are in pretty good agreement with the values that we have obtained analytically. And so it works. For the next example, and this will be the last one we'll do for the day, I want you to try this one. This one says vector A has a magnitude of 20.0 newtons and acts at an angle of 40 degrees below the positive horizontal axis. Vector B has a magnitude of 40.0 newtons and acts at an angle of 50 degrees above the negative x-axis. And it says here to determine the resultant sum of the vectors A plus B. I'd like you to take a minute here just before we actually start and make a sketch of these vectors. When you hit play, we will go over the sketch so everybody is clear on what the orientation of the vectors should be. And then I'll have you go ahead and solve this one on your own. Okay, so your sketch should look a little bit better than this, but hopefully should look something like this. So we have our 20 Newton vector, as it says, 40 degrees below the positive x-axis. And we have our 50 degree vector, 40 newtons above the negative x-axis. And I think I just said 50 degree vector, but our 40 Newton vector, 50 degrees above the negative x-axis here. And so your sketch should look a little something like this. And just for the purposes, I know this particular problem called it vector A and vector B, but since I made up the questions here, let's just go ahead and call this one F1 to keep it similar in style to the last one, and we'll go ahead and we'll call this one F2. I'd like you to do this one completely on your own here. So go ahead and pause this video. I know these take a little while, but go ahead and pause this video and solve this one. And when you're done, hit play, and we'll go over it. Okay, so you should have realized for this problem here that the F1 given in the problem was 20.0 newtons. And so the angle that you needed to use for this, if you remember, we said needed to be referenced to the positive x-axis. And so the angle that you use here is 320 degrees. Now, I think you'll find that if you use negative 40, we'll get the same answers. But I'm always going to make these angle positive just because that's how I want to do it. So our angle is going to be 320 degrees here. And that'll be theta 1. That means our F2 is going to be 40.0 newtons. And the angle is going to be 130 degrees. Theta 2 is 130 degrees. And that's because we want to reference this to the positive x-axis. And so if this is 50 degrees over here, that means it's going to be 130 to the positive x-axis. And of course, we're looking for Fnet. So your first job, again, is to resolve all these vectors into their components. And so we have F1x, F1y, F2x, and F2y. And we write our equations out. F1x is F1 cosine theta. And so that means that's going to be equal to 20.0 newtons times the cosine of 320 degrees. F1y is F1 sine theta. And so that'll be 20.0 newtons times the sine of 320 degrees. F2x is F2 cosine theta. And that'll be equal to F2 40.0 newtons times the cosine of 130 degrees. And F2y, lastly, is F2 sine theta. And that's going to be equal to 40.0 newtons times the sine of 130 degrees. And so if you do that math, 20 times the cosine of 320 should be 15.3 newtons. 20 times the sine of 320, notice that vector is pointing down, so we'd hope that it'll come out as negative. And it does, in fact. You get negative 12.9 newtons. And so notice if you did use the angle of negative 40 degrees, that should have come out the same. 40 times the cosine of 130 is negative 25.7. It makes sense that that component is negative also, because that x component here is pointing left. And 40 times the sine of 130 should have given you 30.6 newtons. And so there are our components. And now we're ready to go ahead and find our components of our net force. So F net x is equal to F1x plus F2x. And so that means F net x, I'll do this down here because the numbers are shorter. F1x is 15.3 newtons. F2x is negative 25.7 newtons. And so that means our F net x is going to give you a value of negative 10.4 newtons. Notice that makes sense because the vector with the x component that was negative is bigger. And then F net y, of course, is going to be F1y plus F2y. And so that is going to be negative 12.9 newtons plus 30.6 newtons. And that will give you an F net y, a y component of your net force equal to 17.7 newtons. And those are the components of our resultant. And now we're pretty much ready to finish this thing out. As we said here, now that we have the two perpendicular components of our resultant, we are just going to use the Pythagorean theorem to find the actual resultant. So we have F net equals the square root of F net x squared plus F net y squared. And when we do this math and we plug in those numbers, we get F net is equal to the square root of negative 10.4 newtons plus 17.7 newtons. We square that as well. We make sure all that's under the radical. And when you do that math and you make sure you square and you make sure you square root, you should get a resultant of 20.5 newtons. Now, it makes sense to some degree that the resultant is not that big here. And that's because, if you notice from the sketch, these two vectors are almost going in the opposite direction. And I think when we show in a second, when we're done with this, the graphical solution, it'll make that obvious. But when these vectors are pointing in the opposite direction, almost, when you add them, you're not going to get a very big resultant. And so our resultant here comes out as 20.5 newtons. And just so we make sure we got the angle here for our direction, because the vector has both a magnitude and a direction here, we have the angle, theta, is equal to the inverse tangent of F net y over F net x. And so we do the inverse tangent of our y, 17.7 newtons, over our x component, which is negative 10.4 newtons. And our angle, if you put it in the calculator, comes out as negative 59.6. But of course, looking at the sketch here, because the 40 Newton vector is bigger, it doesn't really make sense for our resultant to be somewhere down here. We want our resultant to be somewhere over here. And so notice, because the x component is negative, we have to add 180 degrees to that. So negative 59.6 degrees plus 180 degrees gives you an angle of 120.4 degrees. And that's it for the solution of that one. Hopefully you didn't find that one too bad. I think the general idea for these is like, these are not hard. They're just annoying. It's a lot of tedious work. It's a lot of bookkeeping and making sure you're keeping track of all of these symbols and variables and results as you go through the problem. If you look at the graphical solution for this problem, notice here's our analytical solution confirming what we just got. And our graphical solution actually looks something like this. I decided to make the scale pretty small for this one. And so my scale here was 1 centimeter equals 5 newtons, and these values are small. And so we get here a force F1 of 20 newtons down at this angle 40 degrees below the x-axis. And so then we have our 40 Newton vector starting from there at an angle of 130. And notice these are almost in opposite directions. And so that perfectly explains why our resultant is not that big. And our resultant vector, notice when I measured it, I got 4.1 centimeters and then converted it. I got 20.5, right on the money. The angle here ended up being off by a little more, but close enough. The angle came out to 119 degrees. And so it's important to realize while the graphical method is fine, the analytical method is much more reliable because it's giving you, it's giving you an answer with significantly less uncertainty. Okay, so very quickly before we go, we just want to give one note about this, and then that's really it. The question is, in the last problem, they told us to determine the sum of the vectors a plus b. And so the question is, what if they asked us to determine the difference between the vectors a minus b? What on earth are you supposed to do? And so some of you may be thinking, well, the answer lies in the components. What we did was we found the x components for the first vector and the x components for the second vector, and then we added them together. So maybe we can find the x components for those vectors and subtract them, and then do the same with the y components. There's a lot of ways that you might be able to approach this problem. But I think what's important to realize, what I hope everybody is with me on, is that when you have something like this, 5 minus negative 4, that's the same thing as 5 plus 4. And additionally, 5 plus negative 4 is the same thing as 5 minus 4. And so all we really need to do, it's actually not that complicated, is just make use of a basic identity in math. When subtracting vectors, we recognize the identity that a minus b is equal to a plus negative b. And all we have to do is reverse the direction of the vector being subtracted. So basically, instead of doing a minus b, we just make b negative and then do a plus b, and follow the exact same steps that we just followed before. So how do you make a vector reversed in its direction? Well, we simply just add 180 degrees to the angle given for that vector. It's important to realize the sign of a vector, positive or negative, shows you the direction. That's why we flip the direction around. You just simply add 180 degrees to the angle, and now the vector is facing in the opposite direction, thus making it the negative of the original vector being given in the problem. You'll rarely see those come up, but that's an important point here, and I guess sort of ties everything together, and so it's important, I think, that we just took a second to mention that. And with that, that's really it for vector addition. Tomorrow, now we are ready to introduce dynamics and talk about Newton's first law. All right, everybody. Take care.